So Ruben, take it away.
Thank you. So this is joint work with my colleagues Hugo, Simon and Scott at University of Kent. So our motivation comes from two directions largely. Firstly, there is a need for automatic tools for doing refactoring, which in the real world can often involve large numbers of changes across many different files. So this makes it tedious and error-prone for a human to do it often. Error-prone in the sense that it's easy for a person to miss making a particular change which is necessary and which might result in the program not being able to compile, or perhaps even worse, the program would recompile, but you've introduced a subtle bug, so the behavior is not the same. And the other point is that most research on refactoring has typically targeted object-oriented languages. In recent years, there's been some work on refactoring for functional languages such as Haskell and Erlang, but there hasn't been any work specifically targeting automatic refactoring for OCaml. And so OCaml presents its own unique set of challenges. In particular, its module system is very expressive. So this makes refactoring particularly difficult. But there's also some opportunities there because OCaml is becoming much more widely used. If you go on the OCaml website, for example, it will list over 50 companies, I think, who are using OCaml for their software development at the moment. So there's potentially a big win if we can make some automatic refactoring tools for OCaml. As a first step, although ultimately we want to look at refactoring in general, as a first step we're targeting renaming, and particularly renaming value bindings within modules, so top-level value bindings within modules. So modules contain various bindings, usually functions, and so perhaps you want to rename some particular function in some given module. And we think this is a sensible place to start, because if we can get the basics right, then it will mean that we can build on that, and it will be easier and more reliable when we develop further refactorings. But also we believe that looking at renaming already requires solving a lot of the problems which will be relevant to different refactorings and refactorings in general. So we'll be able to really focus on the fundamental problems there. So in our paper, we make 3 contributions in this area. So firstly, we've developed an abstract semantics for a subset of OCaml. And this allows us to characterize exactly what are the changes needed to perform a renaming correctly, in the sense that it won't change the meaning or the behavior of the program. And we also use this semantics to develop a theory of renaming, so a collection of properties that renaming satisfies. Secondly, we formalized our abstract semantics and this renaming theory in the Coq Proofs Assistant. And lastly, we've developed a prototype tool called Rota based on our formal analysis, which can carry out renaming automatically in the full OCaml language. So I'd just like to go through 2 or 3 examples to sort of motivate what are the difficulties in renaming in OCaml's module system. So firstly, here I've got an example which brings together quite a few of the features of OCaml's module system. So firstly, we here have 2 modules called int and string. They each define a type alias t to different types, and they also define a binding of this identifier to string, which is bound to a function which takes a value of the respective type and converts it to a string. We also here have a module type, which we have named stringable. So this just defines an abstract interface to these implementations that we've given. So there's an abstract type t here, and a declaration of a function to string from t to string. Although at this point there's nothing which relates specifically the module type stringable to these other modules, even though they satisfy this implementation. We're not here declaring yet that they satisfy the implementation. Now, next we have a functor. Now, a functor in OCaml is basically a function that takes in modules as arguments and returns a module as a result. So this functor pair it has two parameters, so it takes two modules as arguments, named x and y here, and they are explicitly required to implement this stringable module type. And then what the functor does is it defines a type alias to a pair of the two respective types in the parameters, as well as a toString function which takes a pair of the right kinds of elements of types given by x and y, and then calls the respective toString functions in the arguments to convert those to strings and concatenate them together. Then here we're applying the pair functor to the int and string modules that we have defined earlier, and then binding the result to this identifier p, which then allows us to call the toString function from the module p, which is the result of the functor. Now, a standard binding analysis of this program would tell us that this reference of toString here resolves to the binding of toString in the body of the functor, and if you like, the references of toString in the parameters here, they resolve to this declaration of toString in the module type. Now, if, for example, we wanted to rename the toString function in the body of the functor, this case is fairly straightforward. We just need to find the references to that binding, and specifically that's this one down here. So if we just rename these two instances, that will be correct. We will get a correct program which compiles and behaves in the same way. But if we wanted to instead rename the toString binding here in the int module, things are a bit more complicated. Now, essentially, what we find is that in order to rename this binding correctly, we have to rename a number of other bindings and declarations in the program. So, in particular, the binding of toString in the string module, as well as the declaration of toString in this module type. And that is basically because of this functor application down here. So applying the pair functor to the int and string modules means that we have to consider these bindings and declarations as related, and we'll have to rename them and their references all together. Otherwise, we'll end up with a program that gets rejected by the compiler. So we won't preserve the semantics. So the point to take away here is that in general, in order to work out which identifiers in a program we need to rename to effect a given renaming, we require to take into consideration more information than just the binding structure, the traditional binding structure of the program, which references resolve to which bindings. We also need to take into consideration when different bindings and declarations are related to one another. So in my next example, I want to demonstrate how OCaml's use of shadowing can also introduce some complications. So OCaml allows you to rebind identifiers within a scope. So for example, here we have this module M. It has a module type with a declaration of a string called foo. And then in the implementation of that module, we actually first bind foo to this integer 5, and then we rebind foo to an expression that evaluates to a string. This reference of foo then down here, okay, this is a typo. This should be m.foo. This reference here will resolve to the declaration in the module. And so, again, in this particular example, if we wanted to rename the binding of foo in the module, we would have to rename these other instances, and that kind of works out fine. But in general, that's not enough, because OCaml also allows you to rebind and shadow declarations also in module types. So this is a valid OCaml program where we've shadowed the declaration of foo in the module type. It seems maybe a bit contrived to do this here, but it is a valid OCaml program, so we should try and treat it. And if we wanted to rename the binding of foo here, and we only renamed the instances that I've highlighted previously here, this would actually result in a type incorrect program that would be rejected by the compiler, because what we've actually done in renaming those instances that I've highlighted is we have unshadowed previous bindings and declarations which aren't related, and in fact here the types don't match up. So what this tells us is that we also have to take into account this shadowing information. And when we rename a binding, we have to rename also bindings that it shadows and bindings that shadow it. Lastly, I want to just show how our semantics can capture the notion of encapsulation that OCaml's module system gives us. So in this example, we have a module A, and it has two bindings, foo and bar. This module B then includes the bindings that A has and rebinds bar to a different string. So we've got some shadowing here of this declaration. So as per our previous analysis, we have to relate these two bindings of bar here, the one in B and the one in A. But if instead we had put an explicit module type annotation on the include to only expose the binding of foo and to hide the binding of bar, this would allow us to break the dependency between the two bindings of bar, and so we could then rename those independently. So this is the notion of encapsulation, really, that is expressed in the module system. Of course, now that we've introduced this extra declaration of foo, we have to relate this declaration to the binding of foo in A, and those would have to be renamed together. So in our paper, we've described how we can build an abstract semantics for a fragment of OCaml. Now, I won't go into the details. You can have a look in the paper if you're interested. But essentially, our semantics abstracts program P as a tree. It's abstract syntax tree, but with some extra edges added. These dashed edges would represent the binding resolution information, so which references resolve to which bindings, and these solid arrows represent that information about which declarations and bindings in a program are related to one another. So this allows us to define formally what a valid renaming is, and in particular a renaming is valid precisely when the abstract semantics of the program and its renamed version coincide. And we also show in the paper that the abstract semantics is sound with respect to an operational model of our OCaml fragment. So if two programs have the same abstract semantics, then they are operationally equivalent. So we have our abstract semantics is sensible in that sense. So the renaming theory that we develop based on these semantics has a number of properties. Firstly, as a sanity check, really, we show that the notion of valid renamings induces an equivalence relation on programs. Our main result is that renamings are characterized by their what we call dependencies, and that's this set of bindings and declarations in a program which are all related and must all be renamed altogether or not at all. Given any particular binding in a program, we can construct a renaming that involves that binding, so renames that binding, but also one whose footprint is minimal. And we can also decompose valid renamings into a series of atomic renamings, where an atomic renaming just renames one collection of bindings and declarations which are all related. So our abstract semantics covers quite a large portion of OCaml's module systems. We have modules, module types, functors, functor types. We model opens and includes, aliases of modules and module types, module type constraints, and OCaml's module type extraction feature. The value language that we consider is just one of simple lambda expressions, and in particular we don't consider value types because in our fragment they don't interact with renaming value bindings. What we don't yet model And so because our expressions are just simple lambda expressions, we haven't, for example, modeled complex patterns or records or references or the object system, although that we don't think that would be too difficult to model. Advanced systems of the module system that we don't model are recursive modules, first-class modules, and type-level module aliases. And these we think are quite a bit more complicated to model. So we've implemented this analysis in a prototype tool called Rota, which we've implemented in OCaml, allowing us to reuse the compiler to get access to abstract syntax trees and do type checking, etc. You can install it via OPAM. To run it, you have to tell it which are the source files you want it to run over. You say which binding you want to rename, and you give it a new name. It will then output a patch, a diff. And also optionally information on the dependencies, so this set of all the bindings that it had to rename. There are a couple of situations in which it can fail. So, for example, if you don't give it a fresh name to rename to, it might result in name capture, and in that case, the tool would tell you that this isn't a valid renaming and you can't do it. Sometimes it can happen that renaming would require you to rename a binding which isn't there in the code base that you told the tool about. So also in that case, it would fail. We've evaluated it on a couple of largest test beds, in particular the Jane Street standard library overlay and the OCaml compiler itself. We extracted from these all of the externally visible top-level bindings, and then we asked the tool to rename it to a fresh name, and then we tried applying the resulting patch and recompiling. So our tool was successful in about 70% of cases. So we think this is quite a promising initial result, although there's a bit more of a way to go, obviously. What we found is that in general, the renamings have, on average, quite a small footprint, just a handful of changes over a small number of files, but they can actually be quite large. Here we could see from these figures that actually the Jane Street code is a lot more complicated than the OCaml compiler code, because the maximum footprint that we found was 128 changes over 50 files and involved over 1,000 different bindings to rename. So for in the future, we'd like to extend our semantics and our tool to handle more of OCaml's language features. We'd like to implement other kinds of renamings and allow the user to apply more sophisticated transformations. We'd also like to implement other kinds of refactorings and integrate it into IDEs and OCaml's build systems. And this would make it a really practical and useful tool for OCaml programmers, we think. Thank you very much for listening, and you can find our artifact online.
We have time for one or two quick questions. Please announce your name and affiliation.
Sorry, I'm Michael Norris from CSIRO. I was wondering if you could give an example of a failure. I mean, so 68% seems like quite a low percentage.
Yes. So there are some language features that it doesn't handle.
Okay.
So the semantics handles module type extraction, for example, but that's actually more complicated to deal with in practice. So the tool doesn't deal with it. Also, first-class modules and things like this. So that's a large source of the failing cases. There are some bugs as well, obviously.
Right. And you could, in principle, detect that you were trying to make a change that was going to cause it to fail, or do you just have to unilaterally let it change the file and then test it and then have the compilation fail?
Well, in certain cases, it can detect that it would fail. So the cases that I highlighted, but in the other cases, that's more difficult.
Okay, thank you.
If there are no more questions, then let's thank our speaker.